we do it. This is how we do it. La, 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 la. La, la, la. This is how we do it.
Now we will compute the trajectory of a falling apple using Newton's gravity model without any simplifying assumptions. Newton's law of gravity states that the force between two masses of mass m1 and m2 is given by g times m1 times m2 divided by r squared, where g is the gravitational constant and adjusts for the units used for mass and distance, and r is the distance between the two masses. If we substitute the formula for the force of gravity in Newton's second law of motion, we get an equation for the acceleration of our falling apple. And the equation is A equals g times mass of the earth divided by r squared, where r is the distance between the centers of the earth and the apple. If we write this in functional notation, we get acceleration, a of t as a function of time, equals, and we put a minus in front of the expression because the acceleration is downward, and we replace r by p of t plus r earth, where p of t is the height of the apple above the surface of the earth. This is Newton's model for the trajectory of a falling apple. Let's compare Newton's model to our previous model, which assumed gravity was constant. Before, we had an explicit expression for the velocity of the apple as it falls, and our job was to estimate the unknown position function. With Newton's model, the position function is unknown, the velocity function is also unknown, and we have a formula for the acceleration function, but it contains the unknown function p of t on the right-hand side of the equal sign. However, things aren't as hopeless as they seem. Let's call position and velocity the state variables of the system, and consider a subinterval from ti to ti plus 1, and assume we know the state of the system, i.e. the values of the state variables at time ti. So we know the position at time ti and the velocity at time ti. Note that we can calculate the acceleration at time ti using the model equation for acceleration, since we know the position at time ti. Then we can estimate the values of the state variables at time ti plus 1 using these computational equations. Position at time ti plus 1 equals the position at time ti plus the velocity at time ti times dt, and the velocity at time ti plus 1 equals the velocity at time ti plus the acceleration at time ti times dt. It's as simple as that. So let's write a program. Rather than starting from scratch, we can use our previous program and modify it. So we'll start by saving it as a new program, which we'll call Apple II. Now we're going to need some constants. In particular, we need the gravitational constant, g, which equals, I happen to have here, 6.7 times e to the minus 11. Here's our bird. We need the mass of the Earth, which equals 5.97 e to the 24th power. And we need the radius of the Earth, which equals 6.37 e to the 6th power. Okay. Then we have n equals 5, dt equals 2, so that was a previous problem we did. We're going to initialize P1 to For that problem, we initialize P1 to 20. And we will initialize T1 to 0. And now for the computational equations, T of I plus 1 equals T of I plus dt. That looks good. Now P of I plus 1 equals P of I plus V of I times dt. And we need to initialize, now we need to initialize V of I, so that's V of, we need to initialize V of 1, which equals 0. And now we need to calculate, so we'll just put this on a separate, we'll put this on a separate line. Acceleration at time ti equals the gravitational constant times the mass of the Earth divided by p at time ti plus the radius of the Earth. And that's squared. So the velocity at time ti plus 1 equals the velocity at time ti plus the acceleration at time ti, at, which we just calculated, times dt. And there we have it. Plot t and p. Let's look this over for a minute. Looks good. Let's give it a shot. Not in the load path. It's in the same directory as Apple 1. We put that on the load path before, so I'm surprised to see this error message. You'll have to look into this. We'll add directly to the load path. Now the program should execute. So did it? By Jove, it did. You have to bring up the, whoops! You have to bring up the graph, and instead of falling, this thing went up. So we look at our program and we say, aha, we left out the minus sign. So now we can run the program again and look at the graph, and there it is. That looks bad. It started at 20. What's going on here? We ran for 10 seconds. We didn't want to run for 10 seconds. Aha. We wanted to initialize the altitude to 500. I was working on the wrong problem. So we're doing the falling apple from an altitude of 500. No, n equals 5. There's 5 time intervals. There's 5 subintervals. With 2 seconds, we need to initialize this thing at 500. And then run it. The graph. And now we get the graph that we're looking for. So we have completed the assignment. Now we briefly want to discuss debugging. The first problem we encountered was when we expected Octave to find Apple II and it didn't. We had put the directory for the program on the load path when we created Apple I. However, Octave didn't remember it. The fix is to execute the save path command in the command window. Now let's look at some programming errors. For example, we can create a syntax error by putting 2 pluses where there should be 1. and then executing the program. When OCTAVE detects the syntax error, it prints a message in the command window, and you can look at the command window and see the error message and then fix the problem. So we do that. Then we execute the program and we get the right answer. After the program executes, the variables keep their values and can be examined at the command window. So if we type in P, we'll see the value of the P array, and typing in T gives the value of the T array. So it's useful to be able to examine the variables after the program executes. Now we can also introduce breakpoints into the program by clicking on the red breakpoint icon. When we put a breakpoint in the program runs to the breakpoint and then prints a message on the command window, and we can, or let's say we should be able to look at program variables. But when we try to look at a program variable, it goes on to the next breakpoint. So that's a problem with the OCTAVE interface, which we have to live with. So to get around it, the thing to do is to remove the breakpoint. Whatever you do, don't edit the program with a breakpoint in it. And then to insert in the program a print statement for the variables you want to look at, and reposition the breakpoint following that print statement. Then you can run the program with the breakpoint, and the program variables will be printed in the command window before the breakpoint is encountered. The assignment last week was to write the acceleration equation for a falling apple acted on by constant gravity and atmospheric drag. The equation is shown. Today's assignment is to modify the program in this lesson to compute the trajectory for a falling apple using Newton's gravity model and including the effects of atmospheric drag. Hint, you only need to change one statement. Use these values for the drag coefficient, 0.5, for the density of air, 1.4, for the cross-section of the apple, pi times 0.01 squared, and for the mass of the apple, 0.2 kg. Run the program, plot the velocity graph, and determine the terminal velocity of the apple. That is the velocity where the downward force of gravity equals the upward force of atmospheric drag. Hence, there's no acceleration, and the velocity remains constant for the rest of the fall.
This is how we do